coil of wire is not connected at the ends, and so it does not form a complete electrical circuit. If we tried to make electrons flow around this coil, they would have nowhere to go, and we can tell this is the case because when I drop a magnet through the center, there is no resistance. It falls through the coil as if it were not even there, no slowing down at all. If the resistance to movement we saw with the copper plate was an inherent property of copper, nothing to do with electricity, the magnet should still slow down, even with a disconnected circuit. When I do connect the two ends of the copper wire, now the magnet pauses as soon as it reaches the coil, and it takes a moment to make it all the way through. Electrons can now make a complete orbit around the coil in response to the oncoming magnetic field, and so the magnet slows down as its momentum is converted into electrical current. If I once again disconnect the coil and bridge the circuit with an LED, we can see a better indication of the electricity. The LED is very efficient, so powering it doesn't slow down the magnet quite as much as when the circuit was closed directly. This is a simplified model of how the majority of the world's electricity is generated. There are many different types of power plants, but most of them are just trying to figure out different ways to more efficiently move magnets through coils of wire. Now back to the copper plates. We can't so easily get electricity from these like we can from a coil, but the electrons are still flowing and cause very heavy resistance to a strong magnet. Magnets slow the vehicle down quickly without any surface-to-surface friction that causes damage in conventional braking systems between brake pads and rotors. My favorite tabletop demonstration of magnetic braking is to swing a magnet toward a chunk of copper like a wrecking ball. The magnet loses all of its momentum at the very last moment in a way that almost looks supernatural. It reminds me of a scene in the second Matrix movie where Neo stops bullets in midair. What's really happening is of course the same thing that has happened in my other examples. The magnet's momentum is slowed by opposing magnetic fields generated by the flow of electrons in the copper. And since the electrical energy isn't being collected by a circuit for any useful purpose, it dissipates into the lump of copper as heat. So the copper actually gets warmer every time I swing the magnet toward it, but by such a small amount that measuring the change would be very difficult.